Hello. Uh, in this lecture, we'll give some example of converting a DFA to its corresponding regular expressions. So now first, we'll suppose we are given a DFA. DFA is like that. Suppose Q naught, Q1, and Q2. These are the states given, and inputs A. Here it is a B. It is also B. Load B, and Q2 to Q1 it is also B, and here there is a transition with A. Now we want to find the regular expression corresponding to this DFA. So there is a three states, so three equations will be there, and we have to solve all the equations for Q2 because Q2 is the final state. So what are the equations? So the equations will be Q naught equal to null f or Q naught A or Q1 A or Q2 A. And what is the equation for node or state Q1? Q1 will be Q naught Q1 Q naught B, and equation for state Q2 it will be Q1 B or Q2 B. Now from these three equations we have seen that or it can be looks like this: R is equal to Q plus RP. So by Arden's theorem we know that if the equation is this, R equal to Q plus RP, where R and P are the regular, P and R are regular expressions, then there is an unique solution which is known as Q P star. So from here, if we consider that Q1B is Q and it is Q2, it is Q2 and it is B, P. So now the solution to this will be, so Q2 will be Q1, B and B star. Now if we put this value to the equation Q naught, if we put the value, so sorry, now we can put the value Q1 here. So finally Q2 will be Q naught B, B and B star. Why? Because this is basically the value of Q1 as your Q naught B we put here. So Q2 is basically Q naught B, B and B star we have obtained. Now if we put this value in the equation Q naught, what will happen? So Q naught equal to null and Q naught A or Q1 A, that is we can write Q naught then B A, Q naught, here it will be Q naught, Q1 equal to Q naught B, and that why we replace Q naught B A, right? Now A2 will be replaced by Q2 will be replaced by Q naught B, B or B star and then A, right? Now it will be look like this: null Q naught A or B A or B B B star A. A, B star A. So now it also satisfies this equation R equal to Q plus R P. So the solution will be, so Q naught will be QP star. That means if null or epsilon P star. So basically it will be equivalent to A or BA or B star A its whole star. Now if we put this value into the equation that we have obtained for Q2 in this equation, then the result will be obtained, because we are going to solve the equation for Q2 state, because Q2 is the final state. So final expression, so it will be Q2. So now put the value Q naught A or BA or B star A, right, whole star, then B star. So now this is basically the regular expression corresponding to this DFA. Clear? A, B, B star A, the whole star, B star. So this is our desired regular expression corresponding to this DFA. This is our solution. Now we will give another example. Suppose we are given a DFA, right, like that. So example, suppose it is 2, and we assume that it is example 1. Example 1, now we will example 2. Suppose we are given a DFA Q naught, and it is suppose B, and here it is a Q1, and it will look like this A, and here it will be A, and here it is B. Right? So there is a two state. So we will obtain two equation for this. So one of the equation will be Q naught equal to null of Q naught B or Q1 A. This is one of the equation, and another equation will be Q1 equal to Q naught A or Q1 B. So now from this equation, what we obtain, it is basically equation like that: R equal to Q, it can be R equal to Q or RP. So the solution will be Q1 equal to Q naught A and B star. So Q naught A B star. Now if we put this value into this equation, so what will be Q naught? So now Q naught equal to null Q naught B, and we put this value for Q1, it will be Q naught A B star A, because this is for Q1. Q naught A B star A. Now it also look like this: Q naught B or A B star A, A B star A or B. Now again it will of the form R equal to Q plus R, and this whole thing is P. So the solution for Q naught will be B or A B star A its whole star, and we have to solve this equation for Q1, because Q1 is the final state. So now Q1 will be, we put the value Q naught here, so B or A B star A its whole star and AB star. Yeah. So A, B star. So this is our desired regular expression corresponding to the, so this is basically our solution, or this is our desired regular expression corresponding to this DFA, or deterministic finite automata, right? So now we'll give another definition of another concept, which is homomorphism, which is also a concept, and inverse homomorphism is also there. So homomorphism, first we'll discuss the homomorphism. 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 What is this? And now we can define the homomorphism as a homomorphism is a function, is a function such that H, there is a mapping, that is sigma star to delta star, where sigma star is an alphabet and delta star is another set of alphabet, or delta is another alphabet, sigma is another alphabet, and defined as follows. That is, homomorphism of epsilon is basically epsilon, and for A belongs to the alphabet sigma, H of A, that is homomorphism for this symbol A, is any string in this alphabet, that is delta star. And for A equal to A1, suppose A is any string A1, A2, A3, AN, which belongs to sigma star, where n greater than or equal to 2. Then each homomorphism of A is basically H of A1, H of A2, H of AN. Now, a homomorphism H maps a string A belongs to sigma to another string in delta star by mapping each character of is to a string H of A that belongs to delta star. That means each character of this sigma star will be mapping to a string which is of another symbol that will be taken from this delta star. Yeah. So further we can write a homomorphism. A homomorphism is a function from string to string, or mapping from string to string that respect or the preserve, they respect or preserve the concatenation. They respect concatenation. For any string, suppose xy is the string belongs to sigma star, h of xy is equal to h of x, h of y. Okay. Now, homomorphism, this means, or another way, uh, we can say that homomorphism can be used to transform the languages that is recognized by the finite automata. Obviously, homomorphism is a transform language recognized by a finite automata. So, if a language that is L is a subset of sigma star and it is recognized by a finite automata, it is recognized by finite automata, then image of L. Yeah. So the image, then image of L under homomorphism H, we denote is H of L. Clear? Again I repeat. So if any language that is L, which is a subset of the sigma star, and it is recognized or accepted by this finite automata, then the image L, that is this language, its image L under this homomorphism H, we denote it H of L, which can be written in that way, H of this W or any string such that W belongs to this language. That means every string in L is mapped to another string, that is delta star. So what is the meaning of this? This means every string in L is mapped to another string in delta star. Now we'll give an example, right? Now we will give an example. Suppose we give an example for the homomorphism. Suppose we have a DFA, right? Suppose we have a DFA, right? A over the alphabet, that is sigma is equal to AB, and that recognizes the language, that recognized the language L consisting with even number of A's. Now we define homomorphism as homomorphism H A B, that is that is basically sigma star, 2 0 1 this. Clear? So now we define the homomorphism function is like this, as H of A will be substituted by 0 1, H of B will be 1. What is the meaning of this? It implies that every occurrence of A in a string will be replaced by 0, 1. Similarly, every occurrence of B will be replaced by 1. Now we assume let L contains string like suppose string w1, another string is w1, another string we consider w2. And we know that GFA will accept languages where there is an even number of A's. So we can write any string consisting of AB where there is an even number of A will be accepted. So A, B, or also we can write A, B, B, A. So these are two uh, strings that belongs to this language L we consider. Here also the both of this string contains even number of A's. So it contains even numbers of A. Right? Now, what will be this homomorphism? That means we have defined here that H of L, that is language, will be this H of W, where W belongs to the language. So we can write H of L, that H of W, that is H of string, that is the first string is AAB. So we can write HAAB, which basically written as H of A, H of concatenation, H of B. Now every A will be replaced by 0, 1, as we have defined the mapping that every occurrence of A will be replaced by 0, 1 and every occurrence of B will be replaced by 1. So now we can write that is H of A is equal to 0, 1 and 0, 1 and B is equal to 1. So what actually happened? For this string W1, this will be the language 0, 1, 0, 1, 1, and this language belongs to the these are basically the image of the string AAB. So the new language, that is H of L, that is the new language H of L consists a transformed string. Right. Another example we give. Suppose another example. Suppose this is another example we give. Suppose the homomorphism is defined as 0, 1 to A or B star. We can write 0 or star, or we can also write only the sigma to sigma star, and which is also justified. Where H of 0 is basically defined as AB and H of 1 is defined by BA. Then suppose the string that is 0, any string that is W1 is equal to 0, 0, 1, 1, which actually belongs to this this is a string that is basically accepted by the automata and it belongs to this, right, sigma star. Yeah, so this string belongs to sigma star if we consider that is sigma. So this string basically belongs to sigma star. Now what will be this homomorphism of 0, 0, 1, 1 or H of W? It will be H of 0, H of 0, H of 1, H of 1 concatenation, and H of 0, every occurrence of 0 will be replaced by AB. So AB, AB, and every occurrence of 1 will be replaced by BA. So BA, sorry, it will be BA, BA, and BA. So this is also the transformed string. So this that we have defined is basically the homomorphism. Now we'll give what is inverse homomorphism. Right? Inverse homomorphism. inverse homomorphism. So we can define this inverse homomorphism like that. Given homomorphism, homomorphism, or define the homomorphism like this. These are basically sigma star to delta star as we have defined previously. And L is any language which belongs to this delta star. Clear? So the inverse homomorphism, which is denoted by this, of this language L, which is basically any string which belongs to the sigma star, such that each of homomorphism of that string belongs to the language L. That is, each inverse of the language consists of a string whose homomorphic image, homomorphic image are in L. Clear? So graphically we can write in that way. Suppose this, we assume that this is sigma star, and here suppose it is a another alphabet, that is delta star. Now suppose this, suppose the language L is this, right? So now it can map to here or it can map to here. That means homomorphism of this, that means each of W will be this belongs to this language. Homomorphic of this string belongs to the language L. Clear? And inversely we can say W, that is a string. That string is basically from the set sigma star, generated from the sigma star. So inverse homomorphism is basically the homomorphic images of L. So these are basically the inverse. So each inverse of L are basically this. So you can also write in that way. Right? So it is basically the homomorphic. We can write it as H. There's a mapping from sigma star to H star, and it is basically reverse. Now we'll give an example. Suppose sigma equal to AB and delta is defined as 0, 1, and let h of A is equal to 0, 1 and h of B is equal to 1, 0. So homomorphic is defined. Homomorphic of A, that every occurrence of A will be replaced by 0, 1. Every occurrence of B will be replaced by 1, 0. Now what will be the inverse homomorphism? Right? So inverse homomorphism for the string, that is 1, 0, 0, 1, and inverse homomorphism, suppose another is 0, 1, 0, 1, 1, 0. This 1, 0, 1, 0 and 0, 1, 0, 1 are basically the language. That these are basically the L, right? These are basically the L, that is basically they belongs to here. Clear? These are basically belongs to here in this set, that is delta star. Clear? And we have to find what are the string in this set, that is sigma star. We try to find here what are the string that are basically mapped to here, that is homomorphic map will be the language. So it is nothing but, so look here, 10 means we can replace it by BA, it is B. So we can write B and A. So, so for this string it will be BA. So it will map to here, and for the string is 1001, and another will be 01, that is possible is A. Again 01 means A and 10 means B. So another string from sigma star will be A, which is also mapped to this language where the string will be 01, 01 and 10. Yeah. So these are basically the, we can consider this BA and AB are basically belongs to this set, sigma belongs to or generated by this sigma star. So this is basically the inverse homomorphism. So thank you.